Okay, well, this chapter is called Intermolecular Forces, Liquids, Solids, and Phase Changes. We spent a lot of time talking about gases in chapter 5. We learned things like the ideal gas law, Boyle's law, Charles' law, Gay-Lussac's law, etc. But in this chapter, we're going to deal almost exclusively with liquids and solids. And then towards the end, we'll get into phase changes. Well, I want you to think about a couple things before we even start the lecture. If you think, this chapter's it's not that abundantly clear what the hell is going on in this chapter. Well, if you think about a water molecule, everybody in this class knows the molecular formula of water. And then once we learned nomenclature and molecular formulas, we started looking at Lewis structures. Remember those? Yeah, and we drew a Lewis structure for water where the oxygen had two bonds, one to each hydrogen, and it had two lone pairs. And then we took that even further, and we figured out the molecular geometry of water, which was bent, right? Okay, well, I'm not talking about molecular geometry, but I do want to talk about this Lewis structure just for a second. You notice that these lines here, right, those lines represent bonds, don't they? They represent a bond between oxygen and the two hydrogens. Well, those are the forces that hold the water molecule together. One water molecule is held together by bonds. The bonds in a molecule, we call those intramolecular forces. Intra, right? Intra means within. So intramolecular forces. Okay, so the bonds that actually hold that water molecule together, we call those intramolecular forces because it's a force that's holding those hydrogen atoms to that oxygen. Give me a thumbs up if you follow me just on that, just that idea, nothing more, just that idea. Okay, great. So we have bonds that hold water together, right? Nothing more than that, nothing more than that at all. We're going to take it really slow here. Well, what if I had a glass of water? Okay, what if I had a glass with some water in it? Okay, inside here we have some H2O in the liquid phase. Well, again, you know that there's bonds holding those molecules of water together. But why is it that the water just stays in that glass? Okay? Why isn't it just flying out? And why isn't it all being converted to water in the gaseous phase? And you're like, well, if I have a glass of water, I like to drink my water ice cold. So water boils at, around 100 degrees Celsius at sea level. So why the heck would it escape into the gas phase? Well, in the sample of water, or in that water in the cup, how much water is in there? There's lots of molecules of water, right? There's all kinds of water molecules, H2O, right? If you have 18 milliliters or more, then you've got more than Avogadro's number in there, right? You have all these different water molecules, okay? If I draw a few water molecules out, okay, if I have a water molecule here, another water molecule there, and another water molecule here, I'm really zooming in, okay? I'm zooming in on a small part of that, right? And I have some water molecules, okay? If they're all in the liquid phase, what in the heck is holding them together? Right? Why are they stuck together as water? Why don't they just escape? Because we know that water can be a gas, okay? You're all fully aware of what steam is. There must be something that's holding these molecules together. There must be some kind of glue that's holding these molecules together, right? Okay. Well, the forces that hold the water molecules together, okay, in the liquid phase, those are called intermolecular forces, okay? This right here. Sometimes we abbreviate them IMFs, intermolecular forces, okay? So intramolecular forces, those are the bonds in the molecule, but intermolecular forces are the forces that hold a substance together, okay, in the liquid phase or in the solid phase. Okay, and we're going to look at several examples of this throughout the chapter. What holds molecules together? Now, recall from previous chapters, at ordinary temperatures and pressures, all gases follow the ideal gas law. Everybody is fully aware of PV is equal to nRT. And what was interesting about PV is equal to nRT, or the ideal gas law, is that it was independent of the identity of the gas. Didn't matter if it was sulfur hexafluoride or carbon dioxide or nitrogen, whatever. We could always apply that ideal gas law. However, in gases, when we looked at the ideal gas law, what was one of the assumptions that we made? we assumed that the particles did not interact with each other, right? Remember, we said they were moving in constant random motion, they had elastic collisions. Well, if they had elastic collisions, that's because they're not interacting with each other. We can't make that assumption when we're dealing with liquids and solids. And so there is no equivalent equation of state that can be written to correlate the properties of liquids and solids. Liquids and solids are different from gases. You're aware of that, but let's summarize it here. Molecules are much closer together in liquids and solids than they are in gases, right? In gases, we said that the distance between molecules is quite large. In fact, they're separated by 10 or more molecular diameters. Remember that we said that gases were mostly empty space. Now, if you look at a glass of water on the table, you know that that's not mostly empty space. There's no empty space in there. In liquids and solids, the molecules are all in contact with each other. It's that contact that we're going to talk about. That's what's so important. And that contact, what holds those molecules together when they're contacting each other, that's what intermolecular forces are. And intermolecular forces play a major role in the behavior of liquids and solids, whereas they are negligible in gases. If we go back to that water that I drew on the first slide, on the introduction slide, okay, we said there's some kind of force holding those water molecules together in the liquid phase. But we know that if we supply those molecules with enough energy, they will escape the liquid phase, right? If we heat them up enough, they will escape that liquid phase and they will become a gas, okay? But why is the boiling point of water 100 degrees Celsius? And why is the boiling point of something like ethanol lower? It boils at around 78 degrees Celsius, okay? Why do they have different boiling points? Why do they have different melting points? Well, the macroscopic behavior of liquids and solids, like boiling points, freezing points, etc., is a direct consequence of intermolecular forces. Okay, so to rehash, concepts like melting point, boiling point, what else? Things like density, okay? Refractive index, which is something that we haven't looked at in this class, but anyhow, freezing point, okay, melting point, freezing point, whatever. These are a direct consequence of intermolecular forces, okay? And that's the whole point of the first part of this chapter, okay? All right. Well, let's look at the definition here. And the definition is what a phase is. A phase is a homogeneous part of a system in contact with other parts of a system, but separated from them by a well-defined boundary. Here's a picture of some icebergs floating in water, and you can see that the two phases are certainly separated by a well-defined boundary, right? We have the solid phase, which is ice, and we have the liquid phase, which is water. Before we move on, let's look at some of the properties of solids, liquids, and gases. And again, this is probably review for most of us. This is stuff that we looked at earlier on in the chapter. But if we think about a gas, you might remember that a gas will assume the shape of its container, and it will also take up the entire volume of the container. Why? Why can a gas take up the shape of its container or fill up the container entirely? Because gases are mostly empty space. Therefore, the density of a gas is going to be low, and we know that gases are compressible, right? We can compress gases, okay? And the motion of the molecules is very free, right? They're separated from each other. In the kinetic molecular theory of gases, we even assumed that they moved in, a constant random motion, and they didn't interact with each other. If we look at liquids, liquids have a defined volume, but they don't have a defined shape. They'll take up the shape of their container. Their density is higher, right? Because the molecules are closer together, so we're going to have more molecules per unit volume. Liquids are only slightly compressible, very, very little, and the molecules are going to be able to slide past one another freely. That's why we can pour liquids, right? If you think about pouring a liquid, well, what's happening? Those molecules are sliding past one another as you pour something. And then if we think about a solid, well, that has a definite shape and a definite volume, has a high density, of course, because the molecules are very close to one another, virtually incompressible, and the molecules aren't going to slide past one another, are they? They're going to be stuck in these rigid positions. Another example of a phase, of two phases existing together would be, and this is something that we looked at earlier on in the class, I can't remember exactly which chapter, but there was a chapter where I showed you, we had a volumetric flask in one of the pictures, and it had some bromine in it, Br2. And you remember that in the bottom, there was some Br2, which is actually a liquid in its natural state. But you might remember that the rest of the vessel was kind of filled up with like this reddish color in it. And what that was bromine in the gaseous phase. And so there's a well-defined boundary, isn't there? We could see the puddle of bromine at the bottom, and then we could see the gas being separate from that. So well-defined phases. So let's get into intermolecular forces. Intermolecular forces are the attractive forces between molecules that hold them together. Okay? What's holding the molecules of water together in a glass of water or in a bottle of water? And it involves interactions between charges. You guys remember? Opposites attract, right? We know that plus is going to be attracted to minus. But sometimes the charges are partial and temporary, meaning they're not cations or anions. So if we have partial or temporary charges, this means that's another way of saying not cations or anions. When we have a cation and an anion coming together, that's an ionic bond. Okay, we're not talking about ionic bonds. We're talking about the forces between molecules. Intermolecular forces, which again I like to abbreviate as IMFs, are much weaker than intramolecular forces. Okay, if we go back to our example of water, okay, if I draw some water molecules like this, if I just draw, a smattering of water molecules, I'm just drawing them at random here. They're not any specific orientation or anything. Okay, the forces that are holding these water molecules together, okay, in the liquid phase, let's say it's water in the liquid phase. Okay, it's not ice and it's not steam. The forces that are holding these together, and we're going to talk about exactly what they are, but they are much weaker than the actual forces in the bond, right? The intramolecular forces, the bonds, are much, much stronger. Okay? Forces that hold molecules or ionic solids together, those are covalent or ionic bonds. So intramolecular forces, again, I'm repeating this for about the fourth time today. Those are intramolecular forces, and the forces that hold the molecules, individual molecules together in, the liquid phase or the gaseous phase, those are intermolecular forces. All right, so we've studied ionic bonds and we've studied covalent bonds in dirty detail in this class, but we haven't studied intermolecular forces, and so that's what we're going to cover today. Another comparison of intra versus intermolecular forces. And if you're like, well, Mr. Dion, I still haven't figured out what intermolecular forces are, don't worry, we're going to get there. Okay, and I'm going to go through all of them with you. Let's go back to what we do know. Okay, what we do know are intramolecular forces, right? We know lattice energy in ionic compounds, and we know the bond energy in covalent compounds. If you look at the lattice energy in, let's say, potassium iodide, 649 kilojoules per mole. Okay, that's quite a bit of energy, right? So the lattice energy is high. If you look at the bond strength of a carbon-hydrogen bond, very common bond in nature, 410 kilojoules per mole. Okay, not as strong as the ionic bond, but hey, there's still some strength there. But if we look at intermolecular forces, which again is going to be the focus of this chapter, there's a particular type of intermolecular force called hydrogen bonding. Some of you may have heard of it before. Some of you may not have heard of it before. No problem. We're going to go over it. Well, hydrogen bonding, it's one of the strongest types of intermolecular forces. Okay, it's very strong. It has a value of around 40 kilojoules per mole. It's 10 times weaker than a covalent bond. Okay? 10 times weaker than a covalent bond. So if you're like, what's your point, Mr. Dion? My point is this. A covalent bond, much stronger than an intermolecular force like a hydrogen bond. Much stronger. But and if you're like, well, if they're not that strong, why are you talking about them? Because they're very important. Why? Because all physical properties of compounds can be related back to intermolecular forces, things like melting points and boiling points. Intermolecular forces are those attractive forces between molecules that hold them together at certain temperatures. It involves interactions between charges, not cations and anions. We're not talking about that. We're talking about partial charges. So something that has partial positive charge or partial negative charge. The way we describe partial charge in chemistry class is like this. Okay? You're all fully aware that when we have a cation, we draw a plus, and when we have an anion, we draw a minus. But when something is partial, we use the symbol delta. Okay? Delta means partial. So if we have a partial positive charge, we write delta with a plus. It's a superscript. And if we have a partial negative charge, we write delta with a negative charge like that. And temporary charges. Sometimes you might have heard of these as being described as van der Waals forces. And if you're like, I'm not sure what a van der Waals force is, we're going to define it over the course of this chapter. Again, much weaker than intramolecular forces. Intramolecular forces are bonds, okay? Covalent, and ionic bonds. Something completely different. And they determine the bulk properties of matter. What are bulk properties? Things like melting points, boiling points, densities. We have several types of intermolecular forces. We have ion dipole, dipole-dipole, hydrogen bonds, which is the strongest type of dipole-dipole force, and then we have what are called London dispersion forces. Before we get into all of these different types of intermolecular forces, let's take a look at Coulomb's law just for a second. Okay, intermolecular forces. Let's pick up the pace here and really get into what intermolecular forces are. Intermolecular forces are the attractive forces between molecules that hold them together at certain temperatures. We've already seen this. They involve interactions between charges, partial and temporary charges, sometimes called van der Waals forces. What else do we know? That we used this equation. We used this equation earlier on in Chemistry 1401 to determine lattice energy. We said that lattice energy was equal to a constant multiplied by the product of the charges divided by the distance between atoms. Well, I want us to think about this equation as we move through intermolecular forces. We know that as the charge gets bigger, we have a stronger attraction, and we also know that as the distance gets bigger between the particles, we have a weaker attraction. All right, let me go back to a blank page here just for a second. Good grief, I don't have a lot of room left here, do I? Okay, well, we'll start here. And I just want to break away from the lecture slides just for a second here and go over this really slowly with you. Because I already showed you a slide that you may have noticed had hydrogen bonding on it, okay? And I'm going to walk you through what hydrogen bonding is quickly because it's really important that you understand the concept. But you guys remember we drew a Lewis structure of water that looked like this, okay? H2O. After we learned how to draw the Lewis structure, right, a Lewis structure, we went one further, didn't we? And we started studying valence shell electron pair repulsion theory, didn't we? And from that, we knew that since we had 4 regions of electron density, 2 bonds and 2 lone pairs, that we could draw the molecular geometry of water as being bent, right? It's got a bond angle here, which is less than 109.5 degrees. This is review, okay? We have a lone pair in the back here. We have a lone pair coming out in front like this. So we can draw our water molecule as being bent, and that's why we always draw water as going this way. Then we went a step beyond that, and then we looked at polarity. And we said, are there polar bonds in water? Yes, because we looked at electronegativity. We said that hydrogen had an electronegativity of 2.1, and oxygen had an electronegativity of 3.5. And so since oxygen is more electronegative than hydrogen, there's a dipole going this way, isn't there? And there's a dipole going this way, isn't there? Give me a thumbs up if you follow me thus far. This is just review. Okay, great. All right, some of my students are with me. Good. Well, that dipole, remember the cross at the end of the dipole? That means positive, and the arrowhead is pointed towards the more negative end. So another way we could represent that is like this. We could say we have our water molecule. Instead of writing a dipole arrow like this, I'm going to put delta pluses and delta minus. If oxygen is more electronegative, what was the definition of electronegativity? It's the ability of an atom to pull electron density towards itself in a bond. Okay, so that means that the oxygen is going to be partially negative. It's not an anion, but it's got more of the electron density than the hydrogen does, and therefore the two hydrogens are going to be delta positive, like that. Give me a thumbs up if you follow me on that. Taking baby steps here. Now we got delta pluses and delta minuses. Okay, good. All right, so what happens if now we have a big sample of water, okay? If we have some water in a cup, this is my cup, it's just a big box, okay? I couldn't afford a nice looking cup, okay? If I have another water molecule, let's say around here, okay? And you could draw it any way you want. There's no rhyme or reason to this. I'm just plopping a water molecule down. If this oxygen is delta minus and this hydrogen is delta plus, those charges are the result of permanent dipoles, aren't they? Right? Because there's a difference in electronegativity between hydrogen and oxygen. Well, I'm going to delete those delta minuses and delta pluses. Okay, I'm going to assume that you know that the hydrogens are delta plus and that the oxygens are delta minus. Maybe I should include them again. I'm backtracking. I would make a good politician. Okay, I'm going back on my word. Okay. Anyhow, think about this, you guys. Just bear with or stick with me. Okay. Don't drop out here. This is really important. If I have a partial positive and a partial negative charge that are near each other in a permanent dipole, those are going to be attracted to each other. So what happens is that the lone pair from the oxygen is actually going to interact with that partial positive charge on the hydrogen, and that's what a hydrogen bond is. Okay, this is a hydrogen bond. If you're very astute, which I know you all are, I'll just move this delta minus. If I was to move this, I don't know, move it there like that just to show that it's next to the oxygen. If you're like, hey, Mr. Dion, hey, look, there's a lone pair here and there's a hydrogen there. That's delta positive and delta minus. Couldn't you draw another hydrogen bond like that? Of course you could. Nothing wrong with that at all. Okay, that's a hydrogen bond. Hey, what about if there was another water molecule, Mr. Dion? What if it was like this? What if you had one like this? Could you draw a hydrogen bond, from here to here? Why not? Could you draw one from here to here? Absolutely. Give me a thumbs up if you follow me on the concept of a hydrogen bond. Look, all we're showing is an attraction between plus and minus. Nothing more than that. Does that clear it up a little bit for people who are, maybe thought, hey, it's not that obvious, intermolecular forces? I don't think it is obvious. All right, good, great. Okay, well, let's keep going. We got time. Let's just keep rapping on this piece of paper. I'm gonna have to erase some of my old. This is from our lecture about hybridization, isn't it? Let's just delete it. Okay, we'll end the free. Delete. Okay, let's try another type of intermolecular force. Okay, ready? Who wants to learn a new one? What if you had HCl? Okay, HCl, hydrogen chloride. We learned the molecular formula of hydrogen chloride. Then we drew a Lewis structure, right? And we said, okay, HCl looks something like that. Well, the electronegativity of chlorine is around 3, right? Chlorine has an electronegativity of around 3, and hydrogen has an electronegativity of around 2.1. So that means the difference in electronegativity between the two, right? That looks like crap. My delta En is what? 0.9. So that means there's a dipole in the molecule. I could represent it like this, with an arrow like this, or I could represent it like this. I could say Here's my beautiful Lewis structure. There's a delta minus here, and there's a delta plus here. Give me a thumbs up if you just follow me on that only. Nothing else. Not worried about anything else yet. We're just looking at HCl, discussing the fact that it's got a dipole. We looked at it many times in the class. Okay, well, what happens if I have two HCl molecules that are next to each other? Now, of course, HCl molecules are going to tumble around randomly in space. I'm going to have another one like this. I'm going to have another one over here, another one, like that, another one like this, right? They're going to tumble around randomly. But how random will it be? How random will it really be? If you're like, what do you mean by that? How random will it be? Well, let's think about it. If I have a delta minus on my chlorine and a delta positive over here, doesn't it make sense that if another HCl molecule is in the vicinity, that it would kind of align itself like this? And if you're like, well, why would it align itself like that, Mr. Dion? That seems like a lot of energy for it to just randomly do that. Well, hold the phone. If it did that, then I've got a delta minus next to a delta plus. Then there's going to be an interaction. Didn't mean to use that. I meant to use this. There's going to be an interaction between that delta plus and that delta minus. Okay? This is not a hydrogen bond. This is called a dipole-dipole force, right? Because there is a dipole in this molecule. Okay? That was what is represented by the arrow here. That's a dipole. So since these are polar molecules, right? HCl is a polar molecule. I'm going to have a dipole, right? Because we know there's a dipole here and there's a dipole here. So that's why we call this a dipole force. Give me a thumbs up if that helps. I'm in the business of helping. Okay? I shouldn't be a politician. Okay, we got Joel, we got Violet, Ashley. Okay, good. Great. Good gang. Okay. You guys want me to explain London forces too? Okay, well, let me try. Let's say we have a molecule that's not polar at all. Okay? Let's say we have a molecule of, remember Br2 liquid? Okay, you guys, we learned about bromine, which is one of the diatomic elements. We learned how to draw the Lewis structure of bromine like that. Okay. Is there a dipole in Br2? That's my question to you guys. That's my question. Nothing more than that. Is there a dipole in Br2? Is there a dipole in Br2? Anyone? No. Thanks, Joel. There's no dipole. All right, if I just look at this, there is no delta En between Br and Br, right? The delta En is going to be 0 between bromine and bromine. They have the exact same electronegativity, okay? But if we draw the structure of bromine and we think about all of the electrons involved in this molecule, right? We have bromine, which has 35 electrons, and the other bromine that has 35 electrons, right? What we see in a Lewis structure is nothing more than valence electrons. But we know there's actually a big cloud of electrons around this molecule, okay? There's all these electrons, and it's supposed to be symmetrical, but I'm not an artist. You guys, come on. They don't pay me enough to draw symmetrical shapes, okay? Anyhow, but we have this molecule, bromine, that has this big cloud, and there's electrons everywhere in here, right? There's electrons all over the damn place, okay? Pardon my language. There's electrons here, and they're all evenly spread out, okay? Evenly spread out because there's no dipole. Everything's perfectly balanced. All the electrons are perfectly balanced in this big electron cloud, balanced out by the positive charges in the nuclei. Everybody's hunky-dory. Okay, you ready for Mr. Dion to get real here for a sec? Where are my students? Come on. Okay, can you guys see me? Can my students see me? Okay, good. Okay, now you might laugh at me, okay? But look, this is the easiest way I can explain this. It's actually using my hands, okay? You have the Br2 molecule, right? It's this evenly shaped molecule. All the electrons are perfectly spread out in there. Do electrons stay in the same place all the time? if an electron can move, it will. Okay, electrons are high energy, my friends. So electrons like to move around that cloud, right? My kids like to sing that. I like to move it, okay? You can have that playing in the background while I explain this. Look, if you have that even electron cloud where everything is perfectly balanced, but if all of those electrons are moving, what if, just what if, people, in one instant in time, what if all the electrons ended up on one side of the molecule? Could it happen? There's a probability. What if even there's a probability, and this would be a greater probability, that more of the electrons could end up on one side of the molecule than another, right? First it's all balanced out, then all of a sudden you get more electron density on one side. Couldn't that happen? That could happen, right? Because the probability states that most of the time they will all even themselves out. But what if in just a moment in time, very quickly, fleeting, temporary, okay, a whole bunch of electrons end up just randomly on one side of the molecule? What would it look like? Let's try and draw what the heck that would look like. Okay, where's my slides? Here we are. Can you see my slides again, you guys? Okay, good. So what if in my cloud, if we represent the electrons as being red, I'll try to color code it maybe to make it easier. First, you have them all spread out perfectly. What if all the electrons ended up just on one side of the molecule? Just in a quick, very brief period of time. That means that this side of the molecule is going to be delta minus, and this side is going to have less electrons, so it's going to be delta plus. So if I have something that looks like this, okay, and it's temporary, that means that if another molecule of bromine is in the vicinity, right, if I have another molecule of bromine here, even if all the electrons were evenly spread out here, let's imagine they were all evenly spread out, just perfectly spread out like this. If a delta minus approaches, what's it going to do? Opposites attract, right? And like charges repel. So that's going to push all of these negative charges that are next to the negative end, it's going to push them over here. What's that going to do? That's going to create a dipole in this molecule. And now they're going to be attracted to each other. And that's what a London force is. It's a temporary or brief or a fleeting dipole. So now I've covered dipole-dipole forces, hydrogen bonding, and London forces with you. If you did the Learn Smart, give me a thumbs up if that makes a little bit more sense now. You're like, that cleared it up a little bit, Mr. Dion, the shred. Okay. London forces aren't that easy to explain, really, I find. It's kind of tricky. So hopefully my electron cloud thing, you just have to think about it this way. I mean, you got electrons spread out in a molecule. They're spread out all evenly. But hey, electrons like to move. They like to move it, okay? Electrons are very high energy. This is your mantra. If electrons can move, they will, okay? Electrons like to move around. That's why we have resonance structures, right? Electrons like to move. So if all the electrons move on one side, that creates a temporary dipole. So this is not a permanent dipole. This is a temporary dipole. Temporary dipole. Okay, whereas when we looked at dipole-dipole forces, this is a permanent dipole, right? This is a permanent dipole. It's always stuck there because there's a difference in electronegativity between the hydrogen and the chlorine. And in water, the hydrogen bonding, the dipole in water is also a permanent dipole. Permanent dipole. Okay, kind of gotten away from my slides there for a sec, but I thought that might be helpful for you guys to just kind of stop and smell the roses, right? Anyhow, let's move on and really get into my slides that break down all the different types of intermolecular forces, because there are more than just what we looked at, okay? So far, I showed you, what are the ones we talked about? We talked about dipole-dipole forces, hydrogen bonds, and London forces, which are sometimes called London dispersion forces. We haven't talked about an ion and a dipole. But hey, if you understand what a dipole is, which comes from a polar molecule, and you know what an ion is. We spent enough time talking about ions in this class, right? Then I bet you're going to figure out what an ion dipole force is pretty darn quick. If you take sodium chloride, if you take some sodium chloride, NaCl, solid, and you put it in water, why do you get sodium cations that are aqueous and chloride ions that are aqueous? I mean, they must be stable when they're in an aqueous solution, and they are. And what stabilizes them is an ion dipole force. We know that water is polar, isn't it? I just explained to you why water has an oxygen that is delta minus and hydrogen atoms that are delta plus, because there's a difference in electronegativity between hydrogen and oxygen. Well, the ion dipole force is an electrical interaction between a polar molecule, like water. It could be another polar molecule. This is just the example that's shown here on this slide, okay? And an ion. They're important in aqueous solutions involving ionic compounds. Look, you guys, if you want to understand what an ion dipole force is, I'll tell you what, a picture is worth 1,000 words. If we have a chloride ion, what's the charge on a chloride? It's negative. So you have all these water molecules that surround that chloride when it's in solution, right? That's why it's chloride aqueous, because it's surrounded by water. How is the water molecule going to line up? If you look at this water molecule that I drew in the top corner here, just look at this thing. Isn't this thing beautiful? Look at it. Okay. This is a space-filling model, right? But you can kind of see how one side of the molecule, right, this side here is kind of got more delta plus, right, because you get the two hydrogens pointing down here. Whereas this side of the molecule is more delta minus, because you get the oxygen. Now, oxygen is a bigger atom than hydrogen. We've discussed why that is. So look at the magic that happens here, you guys. Is this a beautiful thing or what? Okay, I've seen some nice stuff in my day, but you know, look, that chloride ion is surrounded by all those water molecules, but look how they line. They don't just randomly line up next to it. You notice that all the hydrogens, which are delta plus, they all stabilize that negative charge on the chloride. What about sodium? Sodium's a cation. It's got a positive charge. Look what the water molecules do. They're like, back it up, back it up, back it up, right? They are all facing the opposite direction. Why? Because oxygen has a partial negative charge. Opposites attract, right? People who think alike stay together and make good partners. Okay, that's not the topic. Okay, this isn't about, you know, relationships. Okay, this is about ion dipole forces. Give me a thumbs up if ion dipole forces make some kind of sense, and if it doesn't, give me a question, and I'd be happy to talk about them even more. I'm serious. If anybody has a question, don't be shy. Okay, don't ever hold back and say, you know, I'm the only person that has that question. That's very rare. Okay, very rare for one person in the class to have a question and nobody else have the exact same question. Okay, if we think that we understand ion dipole forces, well, let's talk about the strength of them. I kind of skipped over that. They're actually moderately strong, in the neighborhood of 10 to 50 kilojoules per mole. So they can even be stronger than a hydrogen bond, which is around 40 kilojoules per mole at a maximum level. Here's a dipole-dipole force, right? I already explained this to you, okay? We said that a dipole-dipole force was the electrical, or the positive minus, interaction between molecular dipoles. So that means you have to be dealing with molecules that have dipoles, okay? So that means you have molecules with permanent dipoles. Okay, that means that you're dealing with polar molecules. We already discussed what polar molecules are. Polar molecules, okay? Molecules. Come on. There we go. Okay? Between polar molecules. They're generally weak. They're in the neighborhood of 3 to 4 kilojoules per mole. It depends on the strength of that dipole. The molecule that's shown here, okay, I don't know if any of you frequent the paint department at Home Depot. Is there anybody in class that likes to just hang out there? You're like, oh, just go to the paint department, you know, it's Thursday. Anyhow, this molecule is called acetone. Acetone. It's oftentimes used as a paint thinner, or sometimes you can use it to clean paint off of, you know, different surfaces. Anyhow, if I draw the Lewis structure of acetone, this is the Lewis structure. It's got a carbon with a double bond to oxygen. The oxygen has 2 lone pairs. It's got 2 more carbons, Okay, and each one of those carbons has 3 hydrogens attached to it. Okay, it looks like this, and this, and this, and this. Right? So here's my acetone molecule. This is called a space filling model. All right, why do we use space filling models? Because it's more of an accurate representation of what the molecule looks like. Okay, if you shrunk yourself down to the molecular or atomic level, you wouldn't see the letter C and the letter H, right? You would see clouds of electrons. So this is kind of like how the clouds of electrons, what they look like. Well, what do we know about oxygen? Oxygen is the second most electronegative element in the periodic table. And so there's going to be a permanent dipole going this way, right? The oxygen is going to be delta minus, and the carbon is going to be left over being delta plus. Carbon-hydrogen bonds, those are nonpolar bonds. They only have a difference in electronegativity of around 0.4. So we don't even worry about those. But we know there's a big old, beautiful, tasty, delicious, permanent dipole right there. So if I have 2 acetone molecules in my bottle of acetone that I'm buying at Home Depot or maybe Lowe's, okay, the molecules are tumbling around randomly in space. If you open up the bottle of acetone, why do those molecules stay in the liquid phase? Why do they just hang out there as a liquid? Why do they just go and evaporate in 1 second? Because there's some kind of force holding them together. What's the force? It's a dipole-dipole force. You have a delta minus here that's going to be attracted to a delta plus here, which we represent as a dash like that. And that's a dipole-dipole force. Right before I showed you with HCl, didn't I? But this is just showing a different molecule. All right, give me a thumbs up if you follow me on that. Dipole-dipole forces, beautiful things. So far we've covered ion dipole, dipole-dipole. Right, in dipole-dipole forces, we're dealing with polar molecule and another polar molecule. All right, well, let's keep going. Here is a sort of a figure just showing the relationship between boiling point and dipole moment. If you're wondering, what the heck is a dipole moment? Okay, a dipole moment. A dipole moment, we use the symbol D, which stands for Debye. Okay, hear you guys. Okay, I'm never gonna ask you to calculate Debyes, okay, in this class. I wouldn't say it's beyond the scope of our class, but it's just not something we cover in Chemistry 1401. All I'm telling you is that the higher the D, higher D equals stronger dipole. Okay, nothing more than that. So what it's saying is you're comparing these 5 molecules, and here are the dipole moments, okay? And you can see the dipole moment is increasing in this direction. So that means that this molecule over here has the strongest dipole, and this guy over here has the propane, just like the propane in your propane tank, the weakest dipole. Okay, weakest dipole. Well, what's the trend? As the dipole moment, the strength of the dipole increases, what happens to boiling point? The boiling point gets higher and higher and higher and higher and higher. Why? Because the separation of charge in, let's say, something like ethylene oxide, the molecule in the middle, right? The red means delta minus. So it's got a little delta minus and it's got a little delta plus here. Okay? Whereas acetonitrile has a bigger delta minus and a bigger delta plus. So it's just based off of the relative strength of the dipole. The stronger your dipole, the higher the boiling point. Nothing more than that. So as molecular polarity increases, dipole moment increases, boiling point is going to increase. Give me a thumbs up if that makes sense. Look, it's just the stronger the partial charge, the stronger the charge, more attracted they're going to be together, right? Which ties in with what? Coulomb's law, right? The force that's holding the molecules together is going to be proportional to their charges divided by distance between molecules. All right, so that's dipole-dipole forces. So my voice is starting to kind of give out here. London dispersion forces. These are the weakest type of intermolecular force. All molecules experience London dispersion forces. Okay? All molecules, even water. Now, the strongest intermolecular force that's experienced between two molecules of water is hydrogen bonding, but they still experience London dispersion forces, and water would also experience dipole-dipole forces. Okay, but London dispersion forces, as I explained to you, you have these two clouds of electrons. Everything's all balanced out. What if in an instantaneous, notice the words they use here, instantaneous, temporary. Another word you could use is fleeting. Right? If you had a romance, but it's fleeting, it didn't last long. Okay, instantaneous, temporary, fleeting dipoles form due to the movement of electrons. Right? Electrons like to move it. Okay. For this reason, this interaction is an induced dipole. Right? Because if all of a sudden this molecule gets a dipole just by random, what's it going to do? It's going to cause a dipole in the other molecule. If you get a delta plus here, it's going to attract all the electrons from the neighboring molecule towards it. That's what induced means, right? It's forcing it to have a dipole present in everything, and it's the weakest of the intermolecular forces, all the way down to 1 kilojoule per mole. What's it based on, right? Why would it be strong sometimes and weak other times? Well, that's based on what's called the polarizability of the molecule. And if you're wondering, what the heck? Polarizability is kind of like, you guys know what a marshmallow is? Okay. Marshmallow is nice and soft and squishy. Okay. Or, anyhow. Polarizability is like the squishiness of the electron cloud. Think about it. If you have something that's big and squishy, you're gonna be able to shape it. If you have what's a good example? If you have a balloon, okay, a balloon is squishy, right? You can squish it with your hands, right? You can squeeze one end and make the other end bigger. So you'd say that's squishy, polarizable. Whereas if you have a basketball, you can squeeze on it really hard, but you're not going to get it to move that far from the spherical shape. So the more polarizable a molecule is, sort of the more squishy the electron cloud is, and the greater ability it has to do stuff like this, where we have more electrons on one side. You see how it's not quite as even? So that's what polarizability means. Kind of a quick and dirty explanation. But, let's just stop for a second and think about what we talked about today. I put a note here in my book, or in my notes, something that's just really important, okay? If you're live lecture right now, if you're here with me, or if you're watching this video at home, think about all these things that we've talked about today. London dispersion forces, dipole-dipole forces, ion dipole forces, hydrogen bonding. In order for you to really understand this stuff, to understand this material thoroughly, you got to understand a lot of things. You got to know things like nomenclature. You've got to know how to draw a Lewis structure. You've got to know how to determine when a molecule is polar or not. You've got to know molecular geometry. So chemistry is an additive class, right? We don't just take what we learned in the previous chapter, throw it in the trash. I even talked about ideal gases today, for Pete's sake. So if you're looking for some encouragement, everything that you learn in chemistry is going to be important later on. Okay, and that's one of the reasons why chemistry is such a good litmus test for professional schools and graduate schools. Okay, it's not just about learning something in 30 minutes and then regurgitating it, 5 minutes later. It's about, learning a large volume of material, being able to recall it several months later, maybe, and then being able to apply it to a problem, right? That's really what those are some of the skills you're really exercising, or if you have those skills, you're flexing them, right, in this class. Anyhow, I just want to kind of stop there and just mention like all the things that you need to know to get this far in class. All right. London dispersion. Atom or molecule's polarizability is dependent on the ease of its electron cloud distortion, right? Its squishiness. The ability of an atom or molecule to be polarizable is going to be based on the size, so the number of electrons, and the shape. Atoms or molecules with larger electron clouds are simply going to be more polarizable than smaller ones. The more electrons present, the greater the polarizability. The longer, also the shape, in terms of the shape, longer and less compact molecules are going to be more polarizable. Well, let's go from here and take a look at a question. This would be a perfectly legitimate question for your next exam. It says both ethane and formaldehyde, which are shown down here at the bottom, have a molar mass of 30 grams per mole. Which would you predict to have a higher boiling point? Let me give you a couple of seconds to think about it. But you've got to look at their structures in order to evaluate it. All right, does anybody have an answer that they want to take a stab at? Would it be ethane, formaldehyde? They have the same boiling point, can't determine it. Two different molecules, same molar mass. All right, I got somebody saying formaldehyde. Somebody says B. Somebody else says formaldehyde. Other people say A. Okay, so we got a plethora of answers here. Let's take a look at the structures. If we look at these structures, the question I want you to ask is polar or non-polar. Okay. Well, if I look at formaldehyde, there's a carbon-oxygen double bond in there, isn't there? So this is a polar bond. So formaldehyde is a polar molecule. In ethane, there are no polar bonds. No polar bonds. Okay. Remember, a carbon-hydrogen bond is non-polar. It's got a delta En of around 0.4, right? Whereas a carbon-oxygen bond is highly polar, right? It's got a delta En of around 1. So ethane is a non-polar molecule. If formaldehyde is a polar molecule, that means it's because it's got a dipole. So if I have two molecules of formaldehyde, I have a delta minus by my oxygen and a delta plus by my carbon. If I have a second molecule of formaldehyde, it's going to interact with the first one and have a dipole-dipole interaction. Whereas the only intermolecular force that ethane is going to experience would be London forces. London forces only because it has no dipole. All right. Give me a thumbs up if that makes some sense once we looked at the solution. So this was just a matter of dipole versus no dipole. The molecule that has a dipole is going to be polar. It's going to have dipole-dipole forces, right? We can even write it down here again. So it's going to experience dipole forces. And ethane is only going to experience London forces. Oh, I just noticed in my notes. I noticed something. I actually wrote down their boiling point. So the boiling point of formaldehyde is negative. Boiling point is negative 19.5 degrees Celsius, and the boiling point of ethane is negative 88. Okay, so the boiling point of formaldehyde is low, but it's much higher than that of ethane. Let's try another question. Here we have the noble gases. Which one of these is going to have the highest boiling point? And if you have an answer, you can just type it in. All right, somebody says D. I think that person is probably in the right vein because all of these atoms are going to have the same shape, aren't they? Right? They're all in the same group, the same family, so they're all going to have the same shape. But what do we know about atomic size? As we go down a group, size increases. So these are large, small, and what do we know about as the electron cloud gets bigger and bigger and bigger? the atom is going to become more polarizable. And the more polarizable the electron cloud is, the greater the instantaneous dipole or the London force will be. And so xenon is going to have the highest boiling point. If you're not following me, let's take a look here. The relationship between polarizability and boiling point. Look at the sizes of these noble gases. When we get down to xenon, it is the largest one. So an atom with a larger electron cloud is going to be more squishy, okay, and more polarizable. All right. So it's just the ability of that atom to distort its electron cloud more than the other four noble gases that are shown in this table. And what do you see? As the polarizability increases, so does boiling point. It goes from 4.2 Kelvin all the way up to 165 Kelvin. Let's talk about London dispersion forces some more. What about if we had linear molecules? Okay, I'm not going to go over the Lewis structures of all of these molecules here as we go from pentane to hexane to heptane, octane, and nonane. These are all hydrocarbons. Hydrocarbons are recovered from fossil fuels, so they're usually isolated in the oil refining process. Well, what do you see here is changing as we go from pentane to hexane to heptane to octane to nonane? The molecules are getting bigger and bigger and bigger, right? They have a higher molar mass. They go from C5H12 to C6H14 to C7H16. You probably noticed that the generic formula of these hydrocarbons is CnH2n plus 2. Well, as the molecules get longer, right, you see how their length is increasing? Length increases. That's going to give you more surface area for the molecules to come into contact with one another. If there's more surface area in between them, they're going to have more London forces, even though there's no polar bonds in a hydrocarbon, right? In a hydrocarbon, there are no polar bonds, but the London forces, the distortion of the electron cloud, can get more and more pronounced as the molecule gets bigger and bigger and bigger. Okay. Another way of describing it would be like this. Okay, and I'm going to describe what's going on in this slide right here that we just looked at. Let's say, you guys know what Velcro is? Probably not. Do they have Velcro anymore? Do you use that? You know what? Let me just turn the camera on. Uh-oh. Did I stop recording? No. Am I still recording? Hope so. You know what's funny is that all of my banter gets recorded and put on YouTube. Anyhow, you guys are probably only the people watching my lectures. Can everybody see me? My favorite type of shoe is Velcro for the win. Yeah, Velcro's great, right, Autumn? I grew up in a poor province in Canada. All we had were Velcro shoes. All right. Anyhow, so let's see here. I went to school with, growing up in southern Nova Scotia is a real poor part of the province. Okay, good. All right. Anyhow, what the hell was I talking about? I said the length of the molecule, the longer the molecule is, the greater the London forces and the harder it is to break those molecules apart to get them to go from the liquid phase to the gaseous phase. Think about it like this, okay? If you had a piece of Velcro 1 inch long, okay, you got a piece of Velcro 1 inch long. The forces that hold the two pieces of Velcro together are the little hooks there, If you took a piece of Velcro that's 1 inch long and I said, hey, I want you to, hey, Blake, I want you to tear this piece of Velcro apart, you'd go like that. That's how much. Would it take some of your bodily energy to rip that 1 inch piece of Velcro apart? Yes, it takes some energy. Okay. Let's say I gave you a piece of Velcro that was 1 mile long. Okay. Like, well, that's ridiculous. Well, let's just say I did. Is it the same force that's holding the Velcro together? Absolutely. But would it take you more energy to break the two pieces of Velcro apart? You'd go, and you're ripping it and you're ripping it and ripping it. It's the same force that was holding those pieces of Velcro together, but the longer it gets, the more energy it's going to take to separate them. Give me a thumbs up if that makes some sense, because that is what was happening on that slide. All right, good. You're like, oh, come on, Mr. Dion, you're not going to ask any Velcro questions on the exam. No, I won't, but the concept still stands. Where's my share screen? I hope you guys are learning something good today. All right, I'm about ready to stop talking here. Where are my slides? What chapter are we on? Chapter 12. Not there yet. Let's go back here. Next class, we'll talk about hydrogen bonding. Anyhow, in more detail. So that's all that's happening. Look, a way of drawing pentane, there's something that we use in organic chemistry, and all of you are going to take organic chemistry with me, right? Wink, wink, nudge, nudge, okay? So pentane, we draw it like this, like 1, 2, 3, 4, 5. If I have a second molecule of pentane like this, there's going to be a certain amount of intermolecular forces or London forces that hold them together. But if I have nonane, there's 9 carbons in nonane. It would look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see it's the same force, the yellow ink that I'm using, but there's more of it. Okay? Again, that's the rationale here. So pentane would be down here. So the longer the chain, the greater the number of London forces, and therefore, yeah, that's it. The boiling point is going to increase. Nothing more than that. All right. Well, what about the shape of a molecule, right? I said that the shape affects the polarizability, doesn't it? This is N-pentane here. It's got a shape like this, like 1, 2, 1, 2, 3, 4, 5. It's a straight chain. It's linear. Okay. And here I have neopentane. It's got a shape that looks like this. Okay. It's kind of like a sphere. And so the longer, less compact molecule is going to be more polarizable, and there's going to be a larger surface area. Think about it. If you pack a bunch of hot dogs together, you're going to have a lot more surface contact than if you pack a bunch of tennis balls together. Okay? That's all that's going on here. So even though they both have the same molar mass, the boiling point of the linear one is going to be higher than the spherical one. It's just about more area for interaction in the linear one and less area for interaction in the spherical one. What type of intermolecular forces exist between each of the following molecules? You know, if you don't understand what's going on in this slide here, this would be a good place for you to, really take a hard look at it over the weekend to make sure you understand what the heck is going on. Because in order to master what's on this slide, you got to be rock solid in your VESPR. Right? You got to be able to draw Lewis structures, draw molecular geometries, and then determine whether a molecule is polar or not. If we look at HBr, we already looked at HCl, and we said that HBr, like HCl, is a polar molecule, right? There's a permanent dipole because bromine is more electronegative than hydrogen. And so if I have 2 molecules of HBr, a delta minus and a delta plus, it's permanent dipoles, right? And so they're going to be attracted to each other, the delta plus and the delta minus. If I draw methane, methane is nonpolar because carbon-hydrogen bonds don't have a dipole. And so they're only going to be held together by induced dipole, which is the exact same thing as London forces. And if you're like, well, come on, Mr. Dion, you got like 3 ways of describing everything. I'm sorry, but that's the way it is. And then if you look at sulfur dioxide, well, sulfur dioxide is a polar molecule, isn't it? Right? It's got a bent shape. Okay. We have a dipole going this way and a dipole going that way. Right? Another way to represent that would be to say, well, I have a delta minus here, I have a delta minus here, and I got a delta plus here. Okay. So if there's a permanent dipole, that means that 2 molecules of sulfur dioxide will be held together by dipole-dipole forces. We also discussed hydrogen bonding. Now, if you understood what I explained to you about hydrogen bonding at the beginning of the lecture, you might be thinking, hey, hydrogen bonding was nothing more than a dipole-dipole, but it is a special type of dipole-dipole interaction, okay, between the lone pair on an oxygen and the delta plus on the hydrogen. Hydrogen bonding, there are three cases where you're going to find hydrogen bonding. It's when you have a bond between a hydrogen and a fluorine, a bond between a hydrogen and an oxygen, or a bond between a hydrogen and a nitrogen. If you don't have one of these three, you, my friend, do not have hydrogen bonding. Okay? You've got to have one of these in order for hydrogen bonding to occur. Okay? Capiche, capoche? Good. Here's hydrogen bonding in water, shown on the left. So this is water. And then this is hydrogen bonding being shown with ammonia over here. Again, nitrogen is more electronegative than hydrogen, so it is delta minus. And here you see the hydrogen bond between the lone pair on the nitrogen with the delta plus of the hydrogen. And that's how we represent it.